everybody. My name is Lucas. I'm a ZK researcher at ZKM. And today I'll give you a brief overview of zkMIPS, what it does and what it is, what it means for ZKM. And, well, I'll start this presentation saying that zkMIPS is how ZKM started. And basically everything else that came after zkMIPS is zkMIPS-based. So this talk is kind of an introduction to everything you're going to see from us this afternoon. And, well, what is zkMIPS? zkMIPS is a general purpose zkVM. It is an attempt, a successful attempt, to implement verifiable computation for MIPS-based programs. So this statement is very dense, so I will break it during this presentation. And first I will start explaining what is a zkVM. I think it's the wrong slides. No, it's not. Okay, so yeah, a zkVM is a proof of knowledge for the correctness of a computation. And a proof of knowledge is a two-party protocol where one of the parties, the prover, wants to convince the verifier that it knows a valid solution to a problem. And in the context of zkVM, the problem is a CPU simulation. The instance for this problem is a program running inside that CPU. And the solution for this instance is the user input plus every CPU state that is generated during the program execution. So usually the solution is private in the sense that there are some things in the user input that the prover doesn't want to reveal to the verifier, and also there are parts of the solution that the verifier doesn't care about, the CPU states. The verifier doesn't want to know the CPU states, they just want to check whether the CPU states, they are well related if they follow the MIPS specification. And that's why we say all of this is private. But in practice, just part of it should be private, should be kept secret from the verifier. Okay, so yeah, proofs of knowledge, they've been around for 40 years, but they received special attention from the crypto community in the last 10, 12 years because they started to be applied to blockchain. And in order to apply proofs of knowledge to blockchain, we must fulfill a few requirements. The first of them is no interaction. We say a proof of knowledge is non-interactive if the prover and the verifier don't have to interact during the proof verification and the proof generation. So the prover don't have to communicate with the verifier to generate the proof, and the verifier don't have to communicate with the prover to verify it. And this makes a lot of sense for blockchain because when we are creating a proof of knowledge for blockchain, we will generate the proof once and we will verify it many times. Many different people will verify it, probably forever. So we cannot expect the prover to communicate with every verifier and every verifier to communicate with the prover. The second requirement is transparency. And this is not mandatory because sometimes, usually when we make a proof transparent, the proof will be bigger and the verification will be is lower. And sometimes we want to avoid this. What I mean by transparency is that the proof correctness does not depend on a trusted third party in the sense that someone don't have to generate some randomness that the prover and the verifier shouldn't know. So transparency and no interaction, they're very similar because when the prover and the verifier, they have to communicate, is usually the case that the verifier is choosing some randomness for the prover, and this randomness guarantees that the proof will be correct. And transparency when a protocol is not transparent, this trusted party is choosing some randomness for the prover and verifier, and this randomness guarantees that the proof is correct. Okay, the third requirement is succinctness. This one is very important, and it is mandatory. A proof is succinct if it can be verified faster than the computation can be executed. This is very important because the functions that we want to verify, they're usually very sophisticated. So we want to verify, like, I don't know, the transition function from layer 2. And this is a lot to verify on chain, for instance. So we want to, instead of run the transition function, just verify that it can be performed off-chain. And we usually do this with matrices and polynomials, because the math behind these objects allows them to encode a lot of information in a way that we can operate over this information, and we can show stuff about this information. And finally, we have zero knowledge, which we see a lot, but it's not mandatory. Not all use cases need zero knowledge. A proof will be zero knowledge if it releases no information about the private inputs. And, well, we support zero knowledge, but again, not all use cases that we support will need zero knowledge. And zero knowledge is also often confused with succinctness, but these two properties, they're very different. Succinctness says more about the verifier interest in the protocol, because the verifier is very, well, it's not very powerful, so it needs to verify the computation really quick. And this is not a problem for the prover, because the prover is usually very powerful, and it can take a lot of time to produce the proof, so it doesn't care that much about performance. And zero knowledge, on the other hand, says more about the prover interest, because the prover might want to keep something secret from the verifier. Next, I need to explain what zkMIPS is and what it does. And to start it, I think we should all agree on what a VM is. And, well, a VM is basically a program that emulates another program, right? So here we have a VM that receives a program and possibly some user inputs, and it will put the program and the inputs inside the memory, and an emulator will modify this memory in a way to simulate the MIPS CPU. And it will be changing this memory constantly until at the end it outputs a signal or a value or a different instance of the MIPS memory. And, well, here, this is a VM. I think everyone agrees on it. Everything knows what this means. But how we prove what's going on inside the VM? First of all, we need to compute the trace record. The trace record is every state computed by the emulator during the program execution. So we will collect the set of internal states, and we'll give it to the prover, together with the initial state of the MIPS memory. And the prover will prove that everything that was performed by the MIPS emulator during the program execution is matching the MIPS CPU specification. So it will show that everything that the emulator did in this step is according to MIPS specification. And at the end, it will output a proof that shows that this output here, it is related to the original MIPS program and possibly to the user inputs. So, yeah, this ZK proof here is showing the correspondence between these two objects. And this is being done inside the prover because the prover models each step of the emulation as a polynomial, compacts this polynomial, and combines all polynomials to show that they are correct. Okay, this is done in 3 steps. So the first step is to just execute the program. we perform a regular VM execution plus some scheduled state logins, meaning we will pause the VM from time to time to collect the internal state of the CPU. We don't have to do this for every internal state of the CPU, just some of them, to define segments of the program, pieces of the program, pieces of the program execution, actually. Then we go to the proving stage, where we use 3 proof systems, Stark, Plonk, and Groff. I'll explain what each of these proof systems do. And when the proof is ready, we will verify it. We can verify it using an off-chain program, which is basically just the software that we use to prove it, or a smart contract. Okay, so how zkMIPS works? Here, you can see that I put the user inputs on the left and the MIPS programs on the right, because I try to keep everything that the verifier knows or everything that the verifier wants to verify on the right, and everything that the verifier doesn't know or everything that it uses to verify something else on the left. The first thing that the zkMIPS software does is to put the user inputs and the MIPS programs inside the memory and hash this memory using a Merkle tree. And this is on the right side because the verifier will have access to this hash, and it can use this hash to verify that the MIPS program is inside the memory. Because this is a Merkle tree, it can isolate the branch that has the program and verify that the program is there. On the left side, the prover will execute the program and will generate the trace record, sorry. And this trace record, it will be basically just the first and the last memory states and program counters of each segment. So it will break the program execution in many pieces, and it would tell us where, what's the memory state of the beginning of each of these segments and where in the program that segment starts to run. And this is enough to prove the entire program later. And then it will hash these memory states as we did with the initial memory state. And the combination of these memory hashes and the program counters we will call image IDs. So here we have image IDs for each segment of the program. We will take these image IDs one at a time, and we will give the image ID of each segment to the Stark prover. This Stark prover, it proves the MIPS transition function. So it will show that everything that's going on inside the segment is allowed by the MIPS specification. And it will output a segment proof for each segment. Once the segment proofs are all ready, we will combine each pair of subsequent proofs. We will combine each odd segment with the next one using the Plonk proof system. So here we have, like, on the left side, the proofs that are being used to prove these image IDs here. And we will combine these 2 proofs into a continuation proof. This continuation proof, it is only possible if these 2 proofs are correct and if the first state of this segment comes after the last segment of the last state of this segment. So if these 2 segments, they match each other, if they continue each other, we can create this continuation proof here. And we will do this for each pair of segment proofs. So in the end, we have like half the number of segments proof. And we will combine these new continuation proofs again. So we have continuation proofs for 4 segments now, instead of only 2. And here, this continuation proof will be possible if these 2 ones are correct, and if the first state of this continuation proof follows the last state of this one. And we will keep on doing this recursively until at the end we have a program proof. But this program proof here, it is a lot to be verified on chain. It is huge, and it is also slow to verify because it is a Planck proof. It is a transparent Planck proof, which makes it even bigger. So we need to compile it to a proof that can be verified on chain. And to do it, we will use the initial memory hash that we generated a few slides over. We'll give these inputs to a Graph16 proof system that outputs a small and constant size proof. And we will have an on-chain proof for this program. And with this on-chain proof, we can verify the execution of the entire program on-chain using our smart contract when we give the initial memory hash for that program. And well, I was going to say a bit more, but the slides are different, so I guess we can skip this. I know this was a lot. Like, I don't expect everyone to understand this just like given this presentation. So in case anyone has any specific question, I'll be around here the entire afternoon and we can talk about this.